Okay, starting at 5.3a, example 1, verify the x values are solutions to the equation. Okay, so here they give us this rotation measurement, pi over 3, and that's radians. Okay, so if I wanted to convert this to degrees, I would just multiply by 180 over pi. Alright, and I get 60 degrees. Okay, so if I build a triangle, I rotate 60 degrees. There's my triangle, 60 degrees there. That's right triangle. That's 30 up here. Sorry for the messy diagram. Across from the 30-degree angle is a length of 1, and across from the 60-degree angle is square root of 3, and then across, or I should say, the hypotenuse is 2, because it's a 30, 60, 90. All right, now I have this equation, secant pi over 3 minus 2 equals 0 that I'm evaluating. All right, so what's secant of pi over 3? Secant is what? Hypotenuse over adjacent. So that's 2 over 1 then. Okay, we could replace the function with. Minus 2 equals 0. So I have 2 minus 2. I get 0 equals 0. That checks off to be true. Same deal with 5 pi over 3. Let's convert this to degrees. Some people don't need to do this. They already can tell what the degree measurement is going to work out to be without doing this. But this helps just in case you have trouble with that. 5 times 60, that's 300 degrees. Alright, so I'm going to rotate 300 degrees all the way around. Okay, and I get that terminal side. Alright, I build a triangle by taking this point here and going straight to the x-axis. That's always the case. And here's my 60-degree angle here. That's my reference angle. All right, you're always working with an acute angle for the triangle. So that's 60, that's 30 then, and that would be 1, that's square root of 3, and that's 2. All right, now the triangle is not to scale, but you have all the information you need to solve the problem. All right, so I have secant now of 5 pi over 3 minus 2 equals 0. And so secant is what? Hypotenuse over adjacent. That's 2 over 1 minus 2. So once again, I get 0 equals 0. Cool. That checks off to be true. I have verified the values work. Okay, before we get into the next example, we're covering a new concept here. And often students find this concept very, very difficult. All right, but once you get it, it's very, very simple. All right, so let's break it down. It says solve sine of x equals a half. All right, well, what does that mean? For what x values is your y value equal to a half? All right, so here I'm along the y-axis here, and these are all the y values that are a half. All right, so here are all the points on the graph or the wave that have a y value of a half. Okay? And so how do I state my solution in a way that it covers all these points? Well, let me use some colors here so you get a good idea of what's going on here. Here is one cycle, all right, to the graph. And within that one cycle, there are 2 points that have a y value of a half. All right, now notice that if I add the period length, all right, to the x value, if I add 2 pi, that takes me to the next value. All right, and if I add 2 pi to that x value here, all right, it takes me to the next value, and so on and so forth. So all I have to do is figure out the points that have that value within one cycle, and then I just add on multiples of the period, and it'll cover all the points that have that y value. So here I have pi over 6, right, for this value. Here's my pi over 6. Here I have 5 pi over 6. That's my x value. All right, now I'm adding 2 pi, but where's this n coming from? Well, if you replace the n with 0, then you just get this point. If I replace it with 1, I'm adding 2 pi on, and I get this point. If I replace it with -1, it's going to take me back to this point. All right, and the same applies for this equation. All right, so this is your solution to this particular problem. All right, now let's do some examples and see how this all works out. Okay, just a reminder, normal period for sine once again is 2 pi, and for sine you could build triangles in all 4 quadrants. All right, now, because there are no asymptotes, okay, some people may be asking, well, why do the quadrants matter? For tangent, you have asymptotes, so that affects the quadrants that you could build the triangles in. We'll get to that example though. First, example 2. All right, first thing you want to do is isolate the trig function. So I'm going to add sine x over here to the left side. And sine x plus sine x is 2 sine x. All right, trying to isolate the trig function once again. So now I subtract square root of 2. Divide by 2. Okay, so now I have this. All right, sine is opposite over hypotenuse. Now, hypotenuse is always positive, so this means that the opposite value must be negative. All right, we're going to use this information now when we build our triangles. In what quadrants is opposite negative and hypotenuse positive? Well, hypotenuse is always positive. What quadrants is opposite negative? That's your y value, so that's going to be quadrants 3 and quadrants 4. All right, so here we have negative square root of 2, negative square root of 2, this is 2, this is 2. Okay, what's the other side going to be? All right, since you multiply this length by square root of 2, you get 2. That's the property of a 45, 45, 90. Okay, so this is also square root of 2 here, and this is square root of 2 as well. All right, now once you've done that, this is where you derive your answer. Okay, so I'm moving by increments of 45 degrees. Okay, or in radians, pi over 4. So this is pi over 4. This is 2 pi over 4. This is 3 pi over 4. This is 4 pi over 4. This is 5 pi over 4. This is 6 pi over 4. 7 pi over 4. And then 8 pi over 4. Okay, so wherever the terminal side lands, all right, that's your radian measure. So I have 5 pi over 4 to start off one of my answers. And then I have 7 pi over 4 to start off my other answer. Okay, so 5 pi over 4 and then 7 pi over 4. All right, now since we're working with sine, what's a normal period for sine? It's 2 pi. So I add 2 pi to each, and I also include n, right? Because I'm adding on multiples of 2 pi, and that's going to cover every cycle in the graph, and actually goes on to infinity. And that's your answer. Okay, let's do another example. All right, same deal as before. One exception though. Normal period for tangent is pi. So we're going to build triangles in quadrants 1 and 2 only. All right, here I'm going to add 1. We want to isolate the trig function to start. divide by 3. I get tangent squared x equals 1/3. And now I'll take the square root both sides. Don't forget the positive and the negative. I have tangent positive negative 1 over the square root of 3. Okay, now tangent is opposite over adjacent. Okay. Okay, now this situation can be a little confusing at first because if I'm just working with the positive case, that means opposite and adjacent are both positive or they're both negative. Now if they're both positive, you're in quadrant 1. If they're both negative, you're in quadrant 3. But once again, for tangent, you don't have to worry about quadrant 3. Okay? So now for negative, opposite could be negative and adjacent will be positive. Okay, but that means you're in quadrant what? 2. And then opposite can be negative and adjacent positive, and that means you're in quadrant 4, which you don't need in this case because once again you're working with tangent. Okay, so I have my 2 right triangles. Opposite is 1. Okay, then I have square root of 3 here. Here I have negative square root of 3. And it should be easy to tell right now that these are 30, 60, 90 triangles. That's going to be 2, 2. Alright, so this is 30 degrees here. That's 30 degrees there. I'm concerned about the rotation to get these terminal sides. So right here, that's 30 degrees. And right here, that's what? That's 150 degrees. Alright, refreshing your memory with radians. This is pi over 6. Then you have 2 pi over 6. Then you have 3 pi over 6. Then you got 4 pi over 6. Okay, now we have 5 pi over 6. And then 6 pi over 6. Sorry for the mess. Okay, but once again, here we're rotating pi over 6. And here we've rotated 5 pi over 6. Okay? And then we're going to add on the period length, which in this case, we're working with tangent, so we add on pi. But we're adding on multiples of pi, so we cover all the solutions. So it's pi n. Alright, so these are your 2 solutions for the problem. Next example here. Alright, here I'm going to add 3. Then I have 4 sine squared x is equal to 3. Divide by 4. I get sine squared x equals 3/4. Alright, then I'm going to take the square root of both sides. Don't forget the positive and the negative. And I get sine of x is equal to positive negative square root of 3 over 2. Okay, now in this scenario I have opposite over hypotenuse, and hypotenuse is always positive. And if I'm working with the positive case, then opposite would be positive. And if I'm working with the negative case, opposite would be negative. Now what quadrants is opposite positive? 1 and 2. What quadrants is opposite negative? Quadrants 3 and 4. Alright, now label my side lengths. That's a square root of 3, square root of 3, negative square root of 3, negative square root of 3. Here I have 2. Okay. And, okay, what's my rotation then? What type of triangles are these? Alright, this is going to be 1. That should stand out. And negative 1 here. So this is 60 degrees. Alright, these are 60 degree angles. Alright, and here's the movement. This is pi over 3 radians. Alright, this is going to be 2 pi over 3 radians. Then we have 3 pi over 3 radians. It's not really to scale, right, but you got the idea. Then I have 4 pi over 3 radians. Then I have 5 pi over 3 radians. And then I have 6 pi over 3 radians. Okay, so there are 2 ways to represent your solution to this problem. All right, bear with me. So rotate 60 degrees, and I get x is equal to pi over 3. And then I have 2 pi over 3. Then I have 4 pi over 3. And then I have 5 pi over 3. All right, for all these solutions then, what do you add? 2 pi times n. Okay. And you could leave your solution like that. When doing this type of problem in the book, it's not going to state the solution this way though. If you write the solution on the test, I'll give you full credit because you know what you're doing. It's just not the most condensed form of the solution. Okay, let me show you what the most condensed form is and what's going on here. As if this problem wasn't already crazy enough, right? Okay, so notice that if I add pi from this terminal side, if I just add pi, I get to this solution here, right? This other solution. If I add pi to this solution here, it takes me to this solution here. All right, so instead of adding 2 pi to this first solution here, you just add pi, all right? And they'll cover all these solutions as well. And then for 2 pi over 3, which we have right here, I'm going to add pi, and that covers this solution as well. All right, so I have x is equal to 2 pi over 3, and I'll only add pi n. So now I've condensed the solution from 4 parts down to 2 parts. All right, once again, if you state this as your solution on the test, full credit. But in your book, you're going to see the solution presented in the most condensed form, which is this right here. All right, this is a pretty crazy problem here in terms of the amount of work you have to do and the things you have to be aware of. All right, it's not that difficult, once again, once you understand everything that's going on. But you're building off of all the knowledge from previous lessons. So if there's any gaps there, please make sure to ask for help so I can help fill those in. We still have 2 more examples though, so let's cover those. All right, for the next one, I'm going to try to isolate the trig functions or push 0 to one side. All right, and I'll factor out cotangent x. Okay, now I have everything in factored form. I'm going to set each factor equal to 0. Cotangent x equals 0. And then here I have cosine squared x minus 2 equals 0. All right, going to add 2 here. Okay, then I have over 1, and I'm working with cosine. Cosine is adjacent over hypotenuse. Okay, so in what quadrants would I build my triangles? All right, hypotenuse is always positive, so if I'm working with the positive case, adjacent is positive, quadrants 1 and 2. If it's negative, or I should say quadrants 1 and 4 to start with. If it's negative, quadrants 2 and 3. Okay, and then I label the sides, square root of 2, negative square root of 2, 1, 1, 1, 1. Okay, now square root of 2 is approximately equal to 1.4. All right, can the length of any of the legs ever be greater than the length of the hypotenuse? No, it can't. So there are no solutions. All right, or the triangles do not exist. You can't have triangles like that. Okay, so no solutions there. Let's go over to cotangent of x equals 0. I could put this over 1, and cotangent is adjacent over opposite. Now, just like tangent, for cotangent, I'm only working in quadrants 1 and 2. All right, what's going on here? Adjacent is 0. Adjacent 0. All right, so we're dealing with this type of situation. What's happening to this length right now as the triangle terminal side continues to rotate? It gets smaller and smaller, right? Until it becomes 0. All right, so that's pi over 2 for our rotation. Now it's pi over 2, and since I'm working with cotangent, I simply add on pi, because the period for cotangent is pi. So we're adding on multiples of pi, pi n. So there's my solution to this problem. All right, so yes, there's a lot going on here now, and some people may have just been able to squeak by in previous lessons or previous chapters, but now with this material here, you really got to know what you're doing. Okay, so if you have any questions, if you need any clarification, please make sure to ask for help. All right, begin the assignment at the bottom of the webpage.